My name is Gary Davis. I'm the Mission Systems Engineer for PACE. And first, I wanted to welcome all of you here. I'm really excited coming from the engineering side of the house to see so many scientists. It's really exciting for us. Sometimes we get stuck in what we're doing and don't get out and see, the bigger picture. So this is really nice. So for today, what I'm going to talk about is the big picture systems engineering, how you design a space mission. And I'll start off with kind of where I came from, and then I'll go through some stories, and then you'll get to relax, and I have a short launch video. It's only 2.5 minutes long, so you can sit through it and watch that. And then afterwards, I'll take credit for all the great work that these folks and everyone else on the mission has done. But as I go along, please feel free to interrupt and ask questions. You can either raise your hand or just shout it out if I'm zoning out and not seeing your hand. This is for you all. And then after all of our talks, we will be available to answer any questions you have. And then if you can't think of your question until later, I will be at the after class thing at the park tonight too. So I'll be happy to answer any questions at any time. All right, so here we go. So who was I? Before PACE, so that's me as a kid on a rocket engine. Most kids like rockets, and so that was down at the Kennedy Space Center. I got to see that when I was a kid. And from there, I pretty much went right to where I am now. No, went through undergraduate, went through graduate school, and then I started working for Goddard right out of grad school. And this picture shows some of the missions that Goddard has done. And so I started off on a mission called TRIM, where I was in charge of, if it were a car, it's basically the gas cap. So it's the fuel gas cap, and you don't want it to leak over time, and that was my little piece. And then I moved on to a mission called MAP, and I was in charge of a whole subsystem. And then I moved to SDO and had a more complicated subsystem. And then from there, I went to MMS, and I had a whole spacecraft. And then after MMS, I moved to OSIRIS-REx, which was not an in-house mission that we built at Goddard. We call in-house missions the one we develop and build ourselves. And then out-of-house missions are ones that contractors make. So I worked on OSIRIS-REx for a while, and now I'm on PACE. Okay, so how do you do a space mission, and what is systems engineering? So this diagram here kind of shows the big picture phases of a space mission. And I'll go through each phase and just talk a little bit about the highlights, just real motherhood and apple pie level stuff, and try to give some PACE examples along the way, but the details are really going to be described by these folks. So at first, you all are the zany scientists, and you have some ideas and some questions. And so those questions get turned into a proposal somehow, and maybe the proposal wins a competition, and you get some seed money, and get to develop what we call a pre-phase A study. And from those initial beginnings is where you start to see how the mission evolves. So for us, 3 groups of scientists with their 3 different instruments: the good, the bad, and the ugly. So where do you start? So before you even want to go to space, you have to look at those green questions to be aware of. Getting to orbit is very expensive. You have to go on a rocket. It's not cheap. Even with a cheap launch vehicle, it's still expensive. If it's expensive, you want the thing you send up there to be reliable, and that adds more expense. So as you figure this cost, the cost management and schedule management of a large mission, it's really important. And it's usually, I will admit, the last thing that engineers, and I'm assuming scientists too, want to think about is the cost and schedule. But it is so important to get that right at the beginning and then keep managing that along the way so you have enough resources to make the mission work. Also, simplicity and robustness. I'll show a slide on this later. As you're conceiving the mission, anything you can think of at the beginning to make it simple and keep it robust will save you, because as the mission progresses, to add these things on at the end is very costly. Finally, launch vehicles are very good these days, but they're not perfect. So that's something that Jeremy and I talk about often is, you could have a really bad day on launch day. It does happen. It's infrequent, but you have to keep that in the back of your mind. So space missions are constantly risky. They take a long time to do. So if you really need to go to space, then you have to think about these blue questions. So what data do you want? That drives your instrument. And Eric can talk to you about how the OCI instrument is so complex because of all the data that science wants. Are you doing a survey mission where you're viewing the entire planet? Do you have individual targets, just little things you want to look at? Do you have ephemeral targets that appear at a certain time and then disappear? So that all matters. What wavelengths do you want, or what resolution do you want? So those define your instrument, and then for your overall mission, do you need one spacecraft? Do you need a whole constellation? What are you trying to see, and when are you trying to see it? That defines your orbit, which can also define your launch vehicle. So all these initial questions start to come together, and you get your initial mission concept. And then finally, who's going to get the data? Who is your customer? And how soon do they need the data? Can they wait 10 years and write their PhD at their leisure? Or do they need data every hour because they're trying to divert ships in certain directions, or some reason they need the data fast? So that defines your ground system and how fast it has to be. So once all those things are done, who's going to do all this stuff for you? Who's making the instrument? Is it a university like UMBC? Is it Ball Aerospace? Is it some company who's never done it before? And then once your instrument is done, who's going to build the spacecraft for you? Who's going to supply the launch vehicle? Who's going to manage that whole process? So you need to think about the bigger picture of what all is happening. And then, do you have any new technology? And as a young engineer, I loved new technology. It's sexy, it's new, it's fun, it's the best you can have. But you have to realize if you're going to take a new technology and try to put it into space, that requires some development and usually some cost. So those are the big picture questions. In terms of changes, and you don't have to read everything on this chart, but just know that as you go along in the mission, you're spending more and more money, and big changes to that mission cost more and more as you go along. So all the studies that have been done show that if you have big changes in the beginning of the mission, they might cost, say, X. But as you get towards the end, it'll cost you 1,000 times more to put those changes in. So that's why so much emphasis is done on the proposal phase and on the pre-phase A to try to get the concept right before you develop it. Here's a picture of the standard NASA playbook for how to manage a mission through its life cycles. And I won't read through every single word on this chart, but it starts with pre-phase A concept study. And then at that point, typically many proposals are reviewed and only a couple win to be formulated. So that's the big arrow at the top, approval for formulation. That's where headquarters gives you your money to do the next phase and do your detailed studies. So then you move along, you might have to develop your technology, you do your preliminary design where that triangle that says PDR, that stands for preliminary design review. So at that point, you pretty much know all the big pieces of your mission and you know generally how they're going to fit together. And you have a big review at headquarters called KDPC. And that's where headquarters and external reviewers look at that preliminary design and say, is it going to work? And is it going to work for the amount of money that you said it's going to take? And that's a very tricky review to get through. If you get through it, then you get funded to do the detailed development and actually fly the mission. So here's the overall mission concept that we came up with. I'm not going to read through it, but you'll see the phases at the bottom, A, B, C, D, and E. So the preliminary design phase, detailed design phase, development phase, and then phase E is operations. And at the end of operations, you have to decommission the spacecraft typically. So who does this? We have this giant org chart that if you look at any of the elements on this, it opens up into more people and more people. I want to say there's roughly 300 people on the PACE mission at this point. So it's very important how you organize your people. And the people are the best resource and the most capable thing we have on the team. Anything you want to do on a space mission, the hardware is not going to do it. The people have to do it. So you're going to have to organize your team in such a way that they're effective and always get the best people that you can get. Okay, so let's say you've done your preliminary design and now we're in the design phase. So I'll take you up into the general top level systems engineering. What are you trying to do? You're trying to trade off three things. You have requirements, that's what the mission has to do. You have your design, which is your hardware and your software of how, what you build. And then you have something called an operations concept, which is how do you actually operate the mission. And those three things keep getting traded during the design, finding out what you can do, how can you optimize, how can you make it cheaper, and how much time you have to go around this circle in both directions and iterate on this. You can get a better and better mission the more you iterate. But you can't get stuck in this phase, because at some point you have to stop designing and actually build the system. So for PACE, these are the big picture items that we have. We have the spacecraft called the space segment. It talks to GPS. So that was one of our decisions. We needed to use the GPS system. We use the TDRS system for S-band communications. We have ground stations on Earth that we can talk to, and we have a launch vehicle to get it all into space. So those are kind of the big picture elements that make up the mission. So we organize all those elements with documentation of requirements. And I know this is the boring part, but the one thing to get out of this is you look at the top of this chart, and that's basically the top level science questions of the mission. So that would be the top documents. And then as you go down, you say, all right, we need an instrument to do these things. We need a spacecraft to do these things. We need a launch vehicle to do these things. And then if you divide up those, take, for example, the spacecraft, we need a power system to do this. We need a mechanical system to do this. Then you take those systems and divide it down more. I need a component to do this. I need a part to do this. So as you go lower and lower in this overall diagram, you get into the real detail, nuts and bolts, literally, of the system. So at the bottom of this diagram, you might have hundreds of drawings, or even thousands of drawings, each having their own requirements and their own things. And then those build up into subsystems, and those build up into elements, and those build up into the whole mission. So our diagram is here. You don't have to read the words, but you see it has the same general shape as the other one. And it's just how we've divided up our requirements. One of our requirements is the orbit. You've seen the orbit before when Jeremy showed that other video. And the reason I wanted to show this is we have our three instruments that have different fields of view. And we have our orbit, and we have the Earth, and this shows how much of the Earth's surface we have. And it was a requirement for us to see, I think, the whole Earth every 2 days. So designing our mission with the orbit allowed us to meet that requirement. So just an example of how those little items flow up. So another big chunk of the mission we have to design is the spacecraft. So what does a spacecraft really have to do? It has to support those three instruments, the good, the bad, and the ugly that you saw before. And it has to point the spacecraft in some strange ways for calibration. And we have to get the data to the ground. And the whole time it has to survive the space environment. So for the space environment, you don't want to be too cold, You don't want to be too hot. You have to keep the instruments in their happy range. You have to survive vibration from the launch vehicle. You have radiation in space. There's atomic oxygen up there. You have MMOD, which is micrometeoroids flying around, so you have a shield to protect yourself from those. So we're trying to design for all these environmental requirements, and we don't want to cost too much, but at the same time, we want to be the best we can for the money that we have. So we're always trading off how much does this thing cost, how much is it going to be versus how good can we make it. And then finally, once the mission is over, we have to do a controlled deorbit so we don't hurt anybody. So all these challenges and all these questions we solve with a pack of M&Ms there. So this is a special M&Ms because in my experience, all the problems are solved with mass, money, and manpower. So those are the three things you need, and they're in finite supply. So it's tricky. So here's the picture of the observatory we came up with. You can see the direction of flight was chosen to shield the instrument from MMOD. And we have an MMOD shield in that flight direction, in the forward direction.
What's MMOD, Gary?
MMOD, micrometeoroids, orbital debris. So instruments are on the aft end of the spacecraft. We have radiators on the cold side to cool off the electronics, and the solar arrays on the hot side. So if you dare to do some pace yoga and you need a stretch, like you can get up, it's okay, you can stand up. And if you are the spacecraft moving forward, the front of you is a shield. And then on one side you have your solar array, that's the warm side. The other side of you is the cold side. And then the OCI instrument would be your backpack, looking down. Okay, so during the design phase, you have lots of challenges, and I just have a few pointed out here. When we were in the design, the federal budget was canceling us every year with the presidential administration, and then Congress would put us back in. So that was a hassle. The OCI instrument, tons of technical challenges that you'll hear Eric describe. And then design to cost, we have a finite budget, so we had to keep our architecture in that cost and schedule box. And I just have one example of a design challenge that maybe you would have thought of, maybe not, but it's called fields of view. So for the spacecraft, we have all these items listed here that have to see certain things. You have your solar array, it needs to see the sun. You have your OCI primary optics, it has to see the Earth. We have star trackers, we have CSSs. There's all these different optical sensors and radiators on the spacecraft, and they each have their own fields of view. Some can't see other things, some want to look in one direction, not in another direction, and it's really tricky just to get everything pointed on the spacecraft the way you want. Coarse sun sensor, sorry. Coarse sun sensor is a little light detector that you put all around the spacecraft, and if the main computer has a glitch and puts you into safe mode, it can see where the sun is, and it tries to point the spacecraft in such a way that the solar panel sees the sun. So it's like our emergency point the right way. So you've done your design, and now it's your chance to build it. We have an acronym called Integration and Test, and Veronica is our lead in that. You're going to hear more details later. So building is the integration in integration and test. Unless you're from the West Coast or Colorado, then they call it ATLO. So this is the fun part, and I have a magic trick that I showed Jeremy. So here's our design, and I saw this design picture, and then I saw the real picture. So that's the magic trick of turning your design into real hardware, and you'll hear the details from Veronica. All right. Then you have the test phase. The test phase is where you verify all of your equipment. And this big diagram out of the NASA Systems Engineering Handbook is called the V diagram. And again, I'm not going to read every word, but you can imagine starting on the top left-hand side of the V. Ooh, we have a science mission. We want to look at A, B, and C. And as you develop the mission, you go down into the V, into the bottom, to all those little piece parts that I talked about. And then at the bottom level, you're doing tests on every single part and every single piece and verifying them at the small level. And then as you come out the other side of the V, all of those little tiny parts are put together into bigger and bigger subassemblies, assemblies, elements, finally at the observatory level. And you do large tests at the end to verify those initial questions. And it's a lot more messy than this diagram shows. And right now, we're kind of climbing out of the bottom of the V. And it's tricky because not everything happens exactly in the same phase. So we would be doing small level tests, big tests, medium tests, all at the same time. And it's a very dynamic time, as Veronica will show you. So along the way, as you're doing these, you run into problems. So this is what I call the campfire graph of how many big problems we have at any one time. So we're kind of on fire, but we're all right. The way we define our problems, we have a PFR, which is called a problem failure report. So if something breaks, we write a problem failure report, and it's red. Red means we don't know what caused the problem, and we don't like that very much. So we do some research and find out what caused the problem. That turns that problem yellow, and we're working on it. Once we've worked on it, we do some risk assessment and turn it green, and then once it's closed out, it turns black. So that's the evolution of our problem system. It's a good process to go through. Sometimes it's slow, but it's very effective in working through our problems.
Is that current? Right. That interfaces problems?
It's about a week old. Yeah. So current.
Does it go to 0 on that right side over there?
Yes, it does. It goes to 0 before launch. However, no, this is a great question. Does it go to 0? It goes to 0 before launch. However, there are some times where something happens and you don't know the root cause, and sometimes you can't find out. So, for example, a computer might reset during a test, and it might be one of your most complicated tests, and you're wondering, why did the processor on the spacecraft reboot? And it might take weeks or months to find that out, and there might be 4 or 5 different reasons. And if we think, oh, it was probably either someone sent a wrong command, or it was a GSE problem, or somebody wiggled a wire when it happened. So sometimes you don't get 100% certainty to close every problem. But on a problem like that, we would try to do a risk assessment and see, if we don't know the exact root cause, what's the effect going to be on orbit, and how likely is it to happen? So that's a great question. Go ahead.
How do you assess the likelihood that something will fail?
How do you assess the likelihood that something will fail? It's a good question, and the only way I can answer that is we treat every problem on a case-by-case basis, and we try to get the experts on that hardware or on that software to kind of give us a thumbs up, thumbs down on how likely they think it is. On rare occasions, you might have data like every single time we turn on this camera, it glitches out. Or maybe 1 out of 100 times it glitches out, and that might be okay. Or maybe it's only happened once in the whole lifetime that we found out. So it's a good question. I don't have a solid answer. I can just say we have to look at each problem.
The right answer is lots of statistics. The real answer is we sometimes trust our guts and listen to our experts. And it's oftentimes a mixture of those two things. As Gary said, money. To get enough statistics to give a real likelihood is usually not feasible for a one-off space mission.
Right. Yeah, that's a good point, Eric. And it's a one-off mission, so it's a unique situation every time. Okay, so you've done your integration, you've done your test. Now it's time for launch. So your team gets divided into 2, and I'll show that in a minute. So our mission is going to be launched on a Falcon 9 built by SpaceX. I won't go through all the details of the trajectory, but we basically launch from Florida, and then the rocket does a right-hand turn, and it flies over Cuba and Central America and heads into its 98-degree inclination from there. And the first stage is going to land back at Kennedy Space Center on land. So I said the team gets divided into two because half get to go to the launch site and the other half stay here at Goddard. So launch site team, that's their environment. If you've been to Cocoa Beach, it's very nice. But Goddard is also very nice because we usually have snow when we launch. So at this time, I have a short video. It's 2.5 minutes long, so we can go through it. I made it myself, so hopefully nobody makes any money on it. Hopefully the sound will work. Let's see.
Lightning red.
Status check. Zero. Terminal count. Atlas systems. Propulsion. Go. Hydraulics. Go. Pneumatics. Go. LO2. Go. Vehicle system engineer.
Go.
Anomaly chief.
AC is go.
Range coordinator. Clear to proceed. Launch director.
LT is go and with permission to launch.
Proceeding with the count. Status check.
Go Atlas. Go Centaur.
Go Osiris Rex.
5, 4, 3, 2, 1. And liftoff of Osiris Rex. Its 7-year mission to boldly go to the asteroid Bennu and back.
So that was Osiris Rex, which, as you know, is on its way back to Earth with its payload of regolith from Bennu. That was a fun mission to work on. I did not get to say go, but I was the last person to see the spacecraft because as they were putting the hatch on the fairing, I snuck in there and took a picture that I wasn't supposed to take. And I told yeah, I told Osiris Rex to make good choices. So, all right. Okay, we're back. Okay, so now you've launched. The spacecraft is working perfectly. Everything's great. So now you're in the operations phase. So for operations, don't get creative. Let operations be boring and just let it do its thing. For us, we're in the polar orbit, and you can see the ground stations have the blue and green circles for our S-band and K-band communications, and we get the data to the ground. And we just want to do this as long as possible, get as much data as we can, let the spacecraft live as long as it can. So after operations, after the spacecraft has been disposed of, now it's back to you, because hopefully we've learned something new with PACE, and you will have more questions. and better, zanier questions. And so for those, we recycle through and we do the next level of mission. So it really comes back to you all to come up with interesting problems for me and everyone to work on. So the last thing I always like to show is here's two pieces of print from the same day. You can read the top one. It wasn't very optimistic. But the bottom phrase, even though it's small, I think it has three important things in it. One is we, which implies a team. Every great thing needs a team to do it. Then it says we started assembly, which means they were actually doing something. They were building it. They were making it happen. And then the last word is today. They didn't wait. They were doing it now. So for any great thing to happen, you need a team that does stuff right now. And this is that team. A lot of the main leaders are right here, so you're lucky to hear from them. So I'll just open up questions for me, and then we'll quickly go to the next. Go ahead.
Gary, what is your major for your undergraduate and graduate?
Undergraduate was aerospace engineering, and graduate was mechanical and aerospace engineering, master's.
That's critical for the job you are doing today?
For the job I'm doing today, I would say no. I would say that when you're a systems engineer, I think it's good to have some discipline engineering experience and having built some hardware yourself. But I don't think it's important what discipline it is, because at the system level, you're dealing with all the disciplines. And you just have to learn and understand and be curious about all of them.
Thank you.
There's a question back here. Go ahead.
So one thing I've recently learned from this is that there's a lot of data and it's not easy to get it all. So my question is sometimes does data get lost and gets deleted off the satellite and never gets down to Earth, or is it always managed?
Good question. We don't have a huge memory that can store data forever. So if we missed some ground contact, we would definitely lose data. We try to size the number of ground contacts we have to always get the data off the memory, but if we go into safe hold for a couple days or have another glitch, we will definitely lose data. So yeah, we lose it sometimes. Go ahead.
How do you make sure when you pick your trajectory that you don't hit anything that's already up there? Another satellite that you
Yes,
know of
that-
or not know about?
That's a great question. There's a service at Goddard called CARA is the acronym, and I can't remember exactly.
Conjunction analysis, I forgot the rest of it is, but at least conjunction analysis is what we normally call it.
So they look at everything that's up there, and if you're going to get close to something, then they take a closer look and do a better analysis of it. And if they think that you're going to collide, they'll ask you to move out of the way if you can. And we do have thrusters on the spacecraft, so we can adjust our orbit, and we have a contingency maneuver in the works. So if we ever get one of those messages that says you have to move out of the way, we have a pre-canned command that we can send up to the spacecraft and have it dodge. That's a great question. Sure.
So the government tracks everything an inch or larger in space at all given times, whether it's made or not. And so it's really the Air Force, it might be Space Force now, it's basically the same thing, are the ones that actually do that. And they're a lot of times the ones that alert NASA or other people, hey, things are going to hit each other. So there's some pre-planning, and then also when it's up there, there's continuous looking at things in space and how they may or may not hit each other.
Do you do the calculations for that launch and orbit and all of that stuff at Goddard, or are you working with other NASA centers?
Yeah, we have a facility at Goddard called the Flight Dynamics Facility, and they design our orbit, and they help us figure out the optimum orbit and determine our maneuvers, how big they have to be. And then for the launch vehicle side, SpaceX and the launch service folks at Kennedy Space Center look at the trajectory for the launch vehicle to make sure they can put us into the orbit that we need. What's the deorbit strategy? So at the end of the mission, once we've run out of all of our operational fuel, which we think will be more than 10 years, even though our requirements are only to last 3 years. After that time, we will do maneuvers to lower our altitude, and then finally the last maneuver targets a zone in the Pacific where there's no one around, and so we put it into the Pacific. All right, go ahead.
Is that true for all NASA satellites?
So, no. For small satellites that will burn up or will have a very small amount of debris that comes back to Earth, they don't need to do a maneuver. So it's expensive to have a propulsion system on board if you don't need it for other reasons. So like CubeSats, they typically burn up in the atmosphere. So we do an analysis of the observatory that looks at every single part and what material it's made of, and we can determine how much is going to come back. And if it's above a certain amount, then it poses a risk to human life, so then we have to target the Pacific. That's a great question. Go ahead.
So, as you said, as we move forward in the project, it's really hard to solve the problems. From your experience, what are the problems that might come during the end of the design process or towards the end of the mission?
Great question. So problems that have cropped up at the end have been things like I'll give an example from here. The HARP instrument. The first time it was built, the entire instrument was completed. It had gone through all of its performance testing, and we brought it to Goddard and did a vibration test on it. And there was a piece that broke off inside the instrument. So that was what I would consider late in the development of that instrument. So luckily, the team here was able to rally and redesign that area of the instrument and rebuild it in time for us to recover and put it on the spacecraft. But something like that is usually what happens at a large level test, especially with an instrument. If you have a failure like that, it can be pretty devastating.
There's also like workmanship problems. People are physically building a satellite, an instrument, and they drop a wrench. Or on our solar cal, on our spare one, somebody accidentally poked through the mesh that is the vent hole for one of the motors, and you have to take the whole thing apart and fix it because they contaminated the lubrication inside of the bearing. So it's like working on your car, but just the stakes are a little bit higher. You don't want to mess up. Well, it's wrenches and screwdrivers and solder.
A follow-up to that, what happens if it cannot be fixed, or is there anything that can we end up like, okay, maybe we can't fix it, or if we don't have more funding for it, so what happens to that project?
That's a great question, and there are projects that have been canceled. Luckily, I haven't been on one of those, but if you search up the records of canceled NASA projects, there are several that get to a certain phase, and then for whatever reason they decide that they either won't work or they can't do it for the money that they said, and headquarters will decide to terminate the project. So that does happen. Go ahead.
Okay, there are also levels in between those very catastrophic situations, right?
Mhm.
There are times when something you design maybe didn't exactly meet the intent of the requirements that you put out for it. Like, let's say you wanted a valve to cycle, 10,000 times for the life of the mission, so you get all the measurements that you want. But you found in a life test unit that you kind of built in parallel with the real one that it only made it half that life. Sometimes when you find those things out, and I've worked on missions before where they'll just kind of derate the mission and say, you can only have this many cycles or this many science measurements, and you can still meet your requirements, but maybe it's not as robust as you had hoped or with as much margin as you had hoped, but you're still able to meet your overall requirements, and I've seen that happen as well.
Regarding cancellation, are you insured against that, or is that just?
We do not carry insurance. I guess What do you mean by insured?
I mean, you're spending a lot of time and money to develop this whole program and machinery. And if this whole thing gets canceled, there's a lot of money going down the drain, I reckon. Is there any way to be insured?
Do you have a plan B?
No, I mean, if headquarters pulled the funding out tomorrow, I don't know. I assume all the government workers would find other projects to work on, but I've never been in that situation, so I don't know.
Usually there's a graceful shutdown too over a number of months. They can't just say like, tomorrow you're canceled, you're all out of jobs. It's not like that. When they do actually cancel, you have to do a lot of cleanup of paperwork and storage and transfer, but yeah, so, and yeah, I think there's, again, scales of what would happen if a failure happens late. We can launch mass models instead of other stuff, so, yeah.
Yeah, the project does everything they can to not be canceled, so. Adding on, I forget the question of what happens when things go bad. A lot of what Gary does and other people around the project is think of all those things. You have people who are like, well, what if, and we have spares, we have different scenarios. So when we do requirements or developing a design, you say, this is how it's supposed to work, but I can fall back to this. Or if a lot of what systems engineering is doing is balancing books. If subsystem X doesn't work, you turn the knob and take from them and give to subsystem Y, and they have to pick it up. You can say that more in instrument terms. If you have multiple instruments that are required to meet a data product, and one instrument isn't as good, well, then that puts the pressure on the other one. And so mission systems and systems engineering in general is balancing those books to make sure that the top level thing can be met. If it's technically instrument, budget, schedule, all of that stuff.
And that's why headquarters tries to have those purple triangles at the top where your mission is approved for the next phase. They try to do that early so that they won't have to cancel you at the end, because they don't want to cancel you either. I mean, they want the mission to succeed. So it's very rare to have a late cancellation.
But if something is cancelled, there is a lot of money wasted, because a lot of the stuff is completely unusable other than for the mission that it was designed for. So the radiation budget instrument was cancelled. I'm hoping to get some really nice detectors from that cancellation. But, the vast majority of the equipment is designed to do that specific thing, and there's no way I can use it, and I can't stick it on an aircraft, so it's just lost.
So who is next to go up? Is it Eric?
I think they're
So let's go away from the depressing talk of cancellation and let's give Eric a huge hand, because the instrument just went through vibration and it appears to be working great. So hats off to Eric.
All right, my name is EricGorman. I am the PACE instrument systems engineer, really focusing on the ocean color instrument. So Jeremy asked me to come here and talk about the instrument. So I've given a few talks over the years to some of the science team members, so I pulled in a few things, and I have a similar presentation to Gary's, but a little more focused, and the question that I like to help answer is, I want to be a PI, what do I have to do? And so that's kind of how I approach this presentation, really presenting to this group of budding scientists, of people who want to get into the field and make a mark and be principal investigators at some point. It's what are the things that you need to do to get there? And so going one level down from what Gary just showed, the question is, how do you transform your science questions into an operational observatory? And before we make that leap, there's a couple of steps in the way, requirements and trades, and I'm going to give examples of what we actually did on the instrument and show how this instrument works as part of all of this. And we got to prototype it, make sure the concept actually works, and of course we build the flight, and then we test it, and we calibrate it, and then we launch it. So going back to the beginning, the most important thing in all of this is agreeing on the right questions that are worth pursuing, and it takes a long time, a lot of really smart people to do that. And so this is the science definition team report. I assume Everybody's read every page of that report in here? Yes? I'm disappointed. You can see it was published, I guess that's the final published date, 2012. And it took years of really smart people like Jeremy and Brian and other folks coming together and saying, what are the questions we want to answer? I'm not trying to shortchange anybody. I know there's lots of smart people who contributed. And these are some of the questions, and I'm sure you've read them, and these are really the foundation that the science community has to agree on, because there has to be a consensus of these are the questions we want answered. Because if you don't agree on that, then let's not waste our time doing anything else. Because what comes from that is really important is, in order to answer these questions, what do I need to do? And typically, you like to build on some sort of heritage, maybe previous space missions, maybe an instrument you've built in your lab and you've put on an airplane. But ultimately, what are the measurements? What are the wavelengths? What is the spectrum? How often do I have to measure? How repeatable? And with PACE OCI mission, we've built on many previous sensors like CZCS, CWIFs, MODIS, VIIRS, and ultimately they said we want hyperspectral data. And I believe Jeremy's gone over a number of the core requirements, and we'll go over it one more time. Actually, let me go back. And of course, from those key measurements come what are the products? So you have to answer the science questions. You need to know the data products that you have that can be analyzed to answer the questions. So this is where the fun really begins, and this is where the engineers come in. And I've actually talked with Jeremy and folks before of it would be fun to do a class on the dialogue between engineering and scientists, especially in the early phase when you're speaking French and German past each other and you can't even communicate. And so this is the critical part, and this is really where we take those science questions, those measurements, and say, all right, how are we going to actually make something physical from this? And so ultimately, what we did is through many iterations of science says, I want hyperspectral. I want to tilt it. I don't want any striping at all in any of my images. And I want to see the whole world, the whole globe once a day. And I say, okay, that's a bit ridiculous. And well, we got it to work. Punchline, eventually. You iterate. We go back and we do the best analysis we can and maybe a little bit of testing in the lab and say, nope, not going to happen. There's no way. And then we go back and we iterate and we iterate. And over time, I get to learn what the science team does and what they're measuring, and that makes me a better engineer. And I think the same thing happens in the other direction where they are starting to understand what engineering speak is, mechanical, electrical, optical types of engineering. So finally, we got that written down, and then that's when the teams can breathe a little bit. At least we're not at each other's throats fighting because we have some sort of agreement of what we're going after. So after that, we move into kind of the next phase, which is the requirements in the trade. So we've got our science requirements, but now we've got engineering requirements, and GaryDavis talked a lot about that. And so what does that actually look like as you move through the mission? So Gary showed phase A, phase B, phase C. And so when we're in that phase A, that's the proposal. What we're doing is system trades, and you can actually see one of our initial proposal ideas right there. It looks kind of small and really boxy. That's because we're not going to waste a lot of time doing a lot of details. It's just how big is it? How much does it weigh? What's the volume of it? How much data comes out of it? Really top level things because you're trading around all these things. The key in that time is to focus on your technology. So also we're doing different trades of where are we going to put some electronics, some computers, what do our optics look like, how are we going to package it, how big is it going to be. You can see a lot of the things that we actually considered building on this mission. The key is on this one, things that always bite you are optics. You have to have those optics settled real quick because those are decisions that you can't change down the road. When we were talking about expensive changes, you can't change an optical design late in the game. It has to be locked in very early, which is why it's so critical to get those science requirements locked in because they're going to drive all of this. And of course the detector, how sensitive it is and what it looks like. So after you move through, you start to see a little more maturity in the design. This was at our mission concept review when we're starting to develop some spacecrafts. I think Beth and Veronica are going to show some of the spacecraft developments as well. But you can see the electronics are growing and shrinking. We're changing radiators, which are the things that cool the instrument. Then we get into the systems requirements review, and that's when we're looking at the detailed engineering design requirements. And again, we changed one more time. We're iterating our design. with the requirements, with the project schedule. And so this was an interesting one as far as change. So we're at our system requirements review, which is maybe a little bit after a third of the way through the mission, and we realized we were broken for a number of reasons. And I'll get into the detectors later, but we had this really challenging requirement to tilt. And at the time in this design, this is called our Dow. That's the box that biases the detector. So if you have a detector, you have to give it a clock to make it read out, and you have to bias it with different voltages. And you tweak all these biases to get the absolute peak performance out of it. And then on top of it, we had our analog to digital converter. So you're detecting a really small signal, few photons, then you got to amplify it, and then you got to send it across a really long harness to this Dow. And then they want us to tilt it, and this harness was going to bend and change. And just by those little capacitance changes of moving a harness, we realized that there was no way we were going to get usable signals across that interface. Because if we did that, you'd be corrupting the science data before it's digitized, and we've got all these really sensitive voltage biases going across that could be corrupted and could carry noise and inject that right into the detector. So we had to stand up and say, we're broken, this isn't working, we've got to find a new solution. So we actually took some steps back, and we imagined what the instrument could look like by co-locating our analog to digital converter with some of those bias electronics. And we iterated and iterated. And we spent more time than project management felt comfortable with, but we didn't stop until we found something that felt reasonable. And some of them were kind of silly. Some of them were okay. I liked this one. I don't think the spacecraft liked this one for obvious reasons. It's a bit hard to tilt that whole thing. This was a fun one. Just make it like a Lazy Susan. Just rotate the whole thing around. Maybe not very stiff. It might wobble a lot when you're vibing it. So finally, we got something that looked reasonable. So we got to this, and we talked to the spacecraft, looked at all of the systems, and said, this could work. So then we took it a step further, and we put a little bit more detail in it. And then ultimately, the PDR, the preliminary design review, you can see we've got something that looks stable. We found a good solution where we have our optical module right here, and I'll go into details of the guts of that in a minute, with that Dow box, and we had a nice stable harness, less than a meter, where we could bolt it in, have everything working nicely, and we found something that we think would work and actually meet the instrument and mission requirements. And then the best thing you want to see as a systems engineer is from PDR, right here, to CDR, the critical design review, nothing changed. Maybe a little more detail, maybe you moved a bracket here or there, but the core architecture was the same, and that's a big deal. So this is our flight design, and this is what it looks like, and here's some of the key systems on it. Let me step back here. So there's your optical module in there, and in there we have a rotating telescope, scans really fast, and I'll show you how that works in a minute. And we have a half-angle mirror, which takes a moving ground scene and slows it down so that you can actually focus it on a static detector. And then in the back, we've got our spectrograph. That's how we take white light and convert it into the wavelengths that everybody's so interested in seeing. Then bolted on the side of that, we've got our solar calibration assembly. Once every 24 hours, we rotate the whole observatory, look at the sun. We've got 3 targets in there, 2 quartz volume diffusers and a fractal black dark target, different radiance levels. So when the sunlight reflects off of it, you can calibrate different points on the dynamic range. We also figured out, using our quartz and some of the spectral lines of the sun, we can do our spectral calibration. One of the tricks you can do if you know the solar spectral signatures and you have a hyperspectral radiometer, you can tease out how the spectral lines are moving on the detector and see if anything is shifting or changing over time. Coming out of that optical module, we have 16 fibers. So our blue and our red wavelengths and the near IR are all in here on the back side, and I'll show that. But our near infrared and shortwave up to the 2.2 micron are actually going over here into this box on the side, which has 32 focal planes, 32 different detectors. And that's where we detect the 940 nanometer up to the 2.2 micron wavelengths. And then on the top, we've got our electronics. We've got a box that's our computer and is our heater, and also what we call housekeeping. It's the card that reads in all the telemetry of temperatures, all the voltages and currents of things that we want to make sure are in spec so that the instrument is healthy. motor control electronics, the electronics that drive the mechanism that spins the telescope, that spins the actuator wheel in there. And then we've got our Dow that takes care of all of our detectors, gives them power and bias. And there's our backside there, all the same stuff. You can see there's looking down the bore sight of the solar cal assembly. There's our blue focal plane assembly and our red focal plane assembly with loop heat pipes that are connected to the radiators, all here on the cold side of the instrument. So how does OCI work? So I've had to sanitize some of this for ITAR, so this is all cleared. So I don't have all of the details in here, but this is a nice cartoon, and if we follow the light path, we can kind of describe how this instrument is architected. So light comes in through our main aperture here. In this case, it's about 90 millimeters, and it hits off of our primary optic. In this case, it's called an OAP, an off-axis parabola. It's some radius of curvature that's going to focus light at some focal length. And we decide the right ones to package everything. So then light bounces and reflects off that, goes through a depolarizer. That was a design choice we made because science does not like polarized light. It'll give you a different signal depending on the polarization state of that light. So we want to scramble stuff. And the right thing to do is put that depolarizer right there. The earlier in the chain you can, the better. But we made a trade because by putting it there, then you have contamination and radiation degradation over time, which is also not good. So we made a trade and said, let's bury our optics so that they can't see the space environment, and we'll put the depolarizer a little downstream, still in a nice spot, to get good scrambled light and still meet spec. So after it passes through that transmissive depolarizer, it hits a flat mirror, and that's only there to package it, because we want to get a nice tight package. And then after the flat, it hits off of our half-angle mirror, which is also on a mechanism. This guy spins at 3 hertz, and it's dual-sided. So the primary, the depolarizer, and the flat mirror make up our rotating telescope. And those 3 optics are spinning 360 RPM continuously in a circle. And then our half-angle mirror is tracking that and spinning 180 RPM, half of the speed. And I'll show you how the dynamics of those work. So that was one of the challenging things of, all right, we want to scan the whole Earth, and we want to take pictures every 40 microseconds, and we want this mechanism to not wobble in any direction such that we can take a nice clean picture. And kudos to the control engineers and to the optical and mechanical engineers who figured out how to build something so stable that it can spin continuously and just take really nice, smooth images. So after the half-angle mirror, we actually focus all of the light onto a slit. And if you put your eyes right there, you'd see a nice panchromatic image, all the colors, white light right there, and it would be a very, very small field of view. But because we want to be a spectrometer, we then take that light and we put in a little field lens, which just pushes the pupil out to enable packaging. Because again, we want enough room to put in all of our mechanical parts. We then hit an optic called a collimator. It's another off-axis parabola, but that takes light that's focusing down and makes it collimated. All the light's going in one direction. It's not diverging or converging. And goes to our back-end spectrograph. So then we have these optical elements called dichroics, which are selectors. It picks the wavelengths of interest. So there's our blue dichroic, and it takes UV up to the green light, and it selects it and puts it down onto a grating. And a grating is an optic that has these mechanical grooves in it. As the light hits the grating, it spreads spectrally, kind of like a prism. And then we have groups of 6 and 7 lenses or so that then focus all of that light onto a CCD, which is the charge-coupled device. It's a silicon detector material. And then integrated front-end electronics, which then takes really, really tiny signals, amplifies them, and then digitizes it. Same design on the red side with the about 600 to 900 nanometers. And then, as I said, we have another off-axis parabola that then images light onto what we call a microlens array. It's a virtual focal plane. So it's a piece of glass that's square on one side and round on the other. And out of the round side comes those 16 fiber optics. And so now you have fiber optics mapping all of the spatial points in the slit that are then going into the back-end SWIR detection system. So if you were to stop OCI from spinning and put your eyes right on that little slit, this is what you would see. Here is Assateague Island. So if anybody's familiar with the area, that's our national park in Maryland, and right above that is Ocean City and Virginia Beach, a little south of that. But that's about to scale according to Google Maps. You would see 16 kilometers in the cross-track dimension and 1 kilometer in the along-track dimension. But because the telescope spins, we've designed it to spin at the exact rate that the spacecraft is moving across the Earth, which is why we got 6 hertz. And it's actually not exactly that number, but it's nice to round up. We rotate so that we are scanning across the whole field of regard to give us a really, really wide swath so that we can make 1 to 2 day global coverage.
Are you, with that 16 pixels, are you resampling the same square of water 16 times as it goes over?
Exactly. Yeah, we're using what's called time delay integration, and I'll show you how that works in a couple slides. Great question. So before we get to the TDI, light has to go through the rotating primary mirror and the rotating half-angle mirror. So this just kind of shows the light path, and I want to note that ground image, and you're going down into the page so that when we take this image and look directly down on it, just remember that the half-angle mirror is physically lower than the primary. So what's actually happening is the rotating telescope is continuously spinning about the whole circle, while the half-angle mirror is dual-sided, spinning about its center axis. And so if we just slow it down, you can see how we're imaging the ground to the rotating telescope, to the half-angle mirror, and such. And then as the rotating telescope spins back around, you're now on ham side B. So it's ham side A, ham side B, every other scan. And then, of course, once a month, once every 24 hours, when we want to look at the sun, we'll open up our door and we'll select the target of interest, and the sun will shine down. We'll go to our rotating primary, to our ham, and then back into our back-end slit. So here's how the grading works. Spectrometer, you have white light from one ground scene. The grading is going to split it up to the wavelengths of interest. So here's what made, one of the many things that made this challenging, and as you asked about the time delay integration, this was our solution to the striping requirement. Striping is a pain, from what I understand, for a lot of oceanographers and marine biologists, because different offsets and different detectors, when you're trying to overlay different scenes, you'll get stripes across your image, and that can be particularly painful. So we came up with a number of ways to solve that, and so that's why we have this really small slit. We came up with a time delay integration where, if you imagine, if you stop and you're just looking at one ground scene, you're collecting all the photons in one bucket, and as the telescope scans to the next ground scene and also moves the light to the next pixel on the detector, take that bucket of photons and you keep dumping it into the next pixel, until it's come to the very end of the detector and you've collected a lot of photons. And so if you imagine we're transferring photons from pixel to pixel, you're getting more and more signal. That's advantageous for many reasons. The big one is noise. Every time you read something out and amplify it, you're introducing noise into the system. But by just summing photons on your detector, it's free. You're just gaining signal with zero noise penalty. And so by doing this, we are able to oversample 128 times. And so we're able to get very, very high signal to noise while spinning very fast. Because if you were to spin that fast and just take one sample, you've got no integration time and you're going to have no photons. So there's a better physical, went off the detector. We don't want to do that. There's a better example if you imagine all the colors just continually moving across the detector and just continuous waterfall of moving photons from pixel to pixel. And so the way that we eliminate striping is actually by having the summation of every one of the pixels at a given band. It's seeing every spatial detector. So you're getting the average of everything, and you only get one answer out. So every wavelength sees every pixel on the detector, and you're getting the sum of all of those offsets. So there will not be striping as a result. And that is how OCI works in a nutshell. So then we get into prototype. After we've done a critical design, let's see if that plays. We then start to cut metal, build a little telescope model. Yeah, it spins pretty fast. You can see the half-angle mirror in there spinning. So we had to figure out how to get all that aligned and stable and take pictures while you're spinning optics that fast. So once we got comfortable with the telescope and the focal planes, then we started building up our prototype, and you can see aligning our optical module installing our focal plane assemblies. There's our Dow, and you can see the rat's nest, because at the end of the day, all a spacecraft and an instrument is a big box of metal and wires. And there's what we call an ETU, engineering test unit or prototype, kind of is something that the engineers can play with and make sure works. And we spent some time doing some system testing in our dark room. You can see a light source that's called an integrating sphere. Makes a nice uniform scene. Those are some cool guys at Goddard. They have a tunable laser. It's called Glamour, and they figured out how to calibrate with NIST, and they can tune this laser from UV all the way to the shortwave infrared, give us a really, really radiometrically stable and accurate calibration source. Couldn't do without that team. And put it in what we call a thermal vacuum test to simulate the space environment. And so here's is it going to play? Let's see. Maybe not. Oh.
Eric, before you go on, just a public thank you to the HARP2 team who came by for like 2 seconds just to say hello.
Oh yeah, let's stop for a second.
This group of people who have been tireless in the recovery of HARP2 and everything. So thank you for coming.
I just want to point out, that's the entire team. Well, that's not true. I have a couple of them up in Goddard. Yeah, one at Goddard. One at Goddard. And one's in Brazil, but there you go. It's not 100 people.
So we had the added challenge of building a hard instrument on a hard space mission. A little thing called COVID hit us about halfway through, which made things a pain. So we had to figure out how to do a lot of this stuff and social distance as best as you can. So this was after we got permission to come back on site. We took our prototype out of the TVAC chamber. So that big white thing there is a thermal vac chamber. And takes a team, put it on this cart, and what you're going to see actually is when we were verifying the stray light and optical performance. What is it? Yeah. I don't think I understand the question.
What's that big white thing?
Oh, yeah. That,
Why don't I take that from
yeah, Veronica, I won't steal all her thunder.
more detail in my section?
Yeah.
And it only takes 10 cups of coffee each for them to move that fast.
Yeah, exactly. So what you saw was them pulling it out of the TVAC chamber, installing our SWIR box with all those detectors. And we named this thing Gator. We love acronyms. It means nothing. It's like Goddard. I'm not remember. Somebody came up with it. But basically, it's our GSE, ground support equipment, that tips and tilts our instrument so that we can put different light sources on it, make sure that we're not leaking light where we're not supposed to, and light's going where it is, and we understand it. And so there we are, taking it off a Gator from a crane and going on to our next test.
Is this still a prototype?
That's all the prototype, yeah. I don't have any cool videos on our flight, but it's similar stuff.
So is ETU essentially a second fully functional system, or just a system to play with?
It is strategic. It can be whatever you want. So here's how it's going to happen if you do systems engineering. You're going to say, management, I need money to build a development unit so that I can prove this thing works before we waste our time doing flight. They'll say, great, do it. And then as soon as you start spending money and get into it, they'll say, well, is there a chance we could fly that? How about we do extra paperwork and spend a little time and go slower just to make sure that it's safe that we could fly it in a bad day, and then you waste all your time doing that and you don't have time for the flight. So you have to be very strategic in the goals you're going after, because it's very easy for everybody on the team to pile on and say, let's do this test, let's do this thing. You say, what are the number 1, 2, and 3 risks and issues we have to resolve, and that's all we're going to do. And I've had to say no, and there's all these things we didn't figure out, but if we were to spend all our time on the ETU, then you're not going to get there. How am I doing on time? I'm almost done. All right. So then you're on your flight component build. So, oh yeah, I had a nice little question. So how do you reliably build an instrument to work in space? You break it into small pieces and you test. So you don't just go all in and build it all up. You have little subsystems and you test them functionally and environmentally, and you slowly build. And so there's some of the OCI testing you can see there in the chambers, like we said, and vibe testing and EMI. And so after that, ta-da, there it is. There's our flight instrument as of yesterday. And I've got a video on my phone that I can show people. It was too big to send. We actually were able to spin the telescope and tilt the thing and look at the science data, and everything was looking pretty good so far. So then after that, we calibrate. We've got a very extensive calibration program using that Glamour laser system I talked about, different polarizers, theodolites, laser trackers, stray light testing, spatial spectral, different filters, and all kinds of spheres and radiometers. If you ever get into the instrument and hardware side in the science world, just remember that no matter how hard your flight instrument is and how well it has to perform, your calibration and your ground support equipment has to be an order of magnitude better. If you're going to prove something that has an SNR of 1,000 to 1, then you need to have an SNR of 10,000 to 1 on your radiometers, or figure out how to at least prove that you're getting 1,000 to 1. Because oftentimes these are much better instruments to calibrate the flight instrument. Otherwise, you don't know what you're looking at. And then, of course, we launch and we commission, like Gary said. So that's what I got. Any questions?
How do you ensure the blue one and the red band consistent? You do have a little bit of overlap.
Yeah,
You have a difference in the overlap. Which one's right?
Yeah, we worked with Jeremy and the science team to pick that wavelength, and we transitioned right around 600 nanometers. There is overlap, and honestly, we can't guarantee consistency because the dichroics, those optics that are the selectors, they're not perfect square filters, so there's some slope, and any of those wavelengths in the transition are on a very steep slope. So any small change, you get a very significant change in signal output. So I know Gerhard, who's our instrument scientist, will be working to cross-calibrate them, but we don't have hard requirements right at that narrow band around 600 nanometers.
So how good can you do?
I'll let you know in about 2 months. We're getting ready to go to TVAC. We have not actually done a blue and a red spectral calibration yet.
But that's in lab, right? Once it's there, how do you...
On orbit, you mean?
But what you test right now is in the lab. Once it's in orbit, how do you know?
What the truth is?
Yeah.
Yeah, using the sun. We've proven through analysis that by using the spectral lines in the sun, we can know exactly what wavelength is hitting what pixel. Spectrally, and then radiometrically, you know, then how much signal are you getting? That's all done through our calibration architecture, which consists of vicarious calibration, buoys in the water, lunar calibration twice a month for long-term radiometric degradation, and solar calibration daily for short-term radiometric degradation.
It's very interesting. How do you use the solar calibration? Doesn't that saturate the detector?
No, it does not, and that was a really challenging thing. I've always said this instrument is threading the needle. We picked the quartz volume diffuser because it actually has a lower BRDF, so it absorbs more of the sun, doesn't reflect as much. So we really had to size our dynamic range, and the sun was actually the limiting factor. So in certain bands, the cloud science said, hey, I actually don't need that upper part of the signal. If it saturates, 2/3 of the way up, we don't care. And so I had the freedom to turn up the gain on electronics, but it was the sun was the limiting factor because we wanted to get a good calibration point. So no, all detectors will see the sun and will not saturate.
Thank you.
Yep. Go ahead.
A follow-up question to that. So you basically check that your instrument performed well over the 3 to whatever years by constantly measuring the sun radiation and the lunar radiation, and you compare it over time to see if your sensors decrease in performance?
Yeah, there's a number of things. So we have the vicarious cal, which is radiometers in the water, so you can do matchups over time to say what's the truth coming out of the water versus what I'm measuring up here. And then we say our initial solar calibration is the truth, and you pin it there, and then every 24 hours you get a new data point. And by doing a rolling average, you can start to see the response of the instrument. Hopefully not too much, but it will go down over time, and then you can always correct back to that initial truth measurement the first one, and then relate it back to the vicarious calibration on the ground. We've also come up with a novel linearity approach using that dim target and that TDI. We're actually doing summing. So we're not reading out the final pixel immediately, so we're actually summing more photons and then reading it out, and then doing another one and summing even more and more. So if you imagine you're reading out 10 photons on one read, and then 20, and then 30, and you can start to build up a response curve, and you can measure out the linearity. So we've come up with a pretty cool, I'm excited, pretty cool way of potentially calibrating the entire dynamic range with the sun. And it seems to be working pretty well in the lab. So.
Vicarious calibration, so I assume that this is like a spot, like a bullet in one place, but you're comparing it to like a set like what pixel or like 3 by 3, like how exactly is that?
You'll get an hour of it on Friday morning.
You showed a slide that was like just the optical movement of light through the sensor.
Yeah.
How much, when you started this project, like, if you were just brainstorming what it was going to look like, how similar would it have looked to that thing? Like, is that how all, is that what you expected it to look like, or is that completely like novel?
Yeah, so the spinning of the telescope with the half-angle mirror, that's been done before. That's how VIIRS works. They just move a lot slower. So we knew it was going to look something like that. We knew we were going to use the slit grading spectrometer, and that was about it. And then how it finally got packaged and put together was stuff we had to iterate through. And honestly, we were broken. Before I did that tilt trade, before that, our detectors were broken. We realized we were reading them out way too fast and were never going to work. So we had to go back and redesign the detectors and make some optical tweaks along the way before we even got to that tilt trade that I showed. I'll see you next.
You didn't talk at all about the shortwave infrared.
I didn't. I'm strategically focused on the Visnear for time and ITAR mainly. I didn't have any ITAR cleared shortwave stuff. I apologize. I saw one over here.
Yeah, I was going to ask, how do you kind of balance between wanting to build on the heritage of what you know works already versus pushing the envelope of demonstrating new technology in space? And who like ultimately makes that call? Is that the engineering team that puts their foot down and is like, we can't do it? Or the science team says, you have to do this? You know what I mean?
Yeah, no, I'll answer personally, and then I'll think of another answer. For me, when I started this, I was more naive. So I was like, we got to do the new technology. So cool. And then I got beat up a little bit. So the balance is, if I were to do this again, or if I were to work on another flight mission, have you heard of TRL, Technology Readiness Level? Okay, it really comes down to that. And it's, when you're in that proposal phase, if you haven't gone end-to-end with some sort of breadboard development, you've put light in, you've gotten digital numbers out, and whoever scientist is in charge has made a product. Maybe it's not perfect, but at least you've gone end-to-end. Your instrument's not TRL-6, and it's not ready for a flight mission, I think is the bottom line. And if you are, you can dance around it and say, well, it's close enough, it's good enough, and you might be right, and it's how confident are you that you can make it happen on a flight schedule with 200 engineers saying, where are my requirements every day? But if you want to be safe and know that it's good, you've made a data product with some sort of development thing. And with whatever technology you've used to do that, that's when you know you're good to go to the next level. Now, that sounds really naive as well. I'm sure these guys are laughing because that's not always how things get done. People oversell proposals. And that's at the risk of the PI, the project manager, and the lead engineers who have to be honest with each other and say, this tech isn't where it needs to be, so let's address that and fix it.
And if I can add on a little bit to what Eric said, at the mission level, there's really a fine line with how much new technology you want. And your question is perfect. Because at NASA, we're almost expected to be doing the most challenging instruments we can dream up, which is OCI, and also on the spacecraft side, maybe put in some new technology because it's almost expected. So along the lines, we've say one new technology on the spacecraft side that we are flying that's new, and one that was almost forced on us by outside organizations.
Talk about that a little bit.
Hmm?
I'm going to talk about that.
And Beth will talk about that. And then there was another new technology that we almost flew, and then we decided it was too much cost and too complicated, and we scrapped that and went back to the tried and true. So it's a dynamic case-by-case scenario, but it's a great question.
But there's no such thing as heritage. That, I think that's what you really need to understand, is because we are trying to build to print, so build the exact same thing we just built, and it's different people. We've lost the recipe. Some of the parts don't exist anymore. We cannot buy them again, and because of that, we have to redesign things, and that changes slightly, and then that affects something else. So I feel like unless you built it yesterday and today, there's no such thing as heritage. If you built it more than 5 years ago, it's not the same. It will not be the same, and it'll act differently.
There's a documentary on Netflix about the Boeing MAX 8, and it goes through, I mean, it's fascinating to watch, and you might not want to fly on that plane, but it, in a nutshell, shows this, what Beth just described of, let's make one change. You know, they wanted to put a bigger engine on and move it up a little bit, and it changed the CG and the center of aerodynamics, and all of a sudden it rippled through the whole system, how this one thing, and they claimed heritage, and certainly it ended up not being. So then they added on that rudder, and the rest is history. And so, but that is systems engineering for complex spacecraft, planes in a nutshell. You think you can change one thing, and it breaks everything.
You mentioned overcoming strapping with time, delayed integration. I guess everything has its trade-offs. Would that cause smearing the spatial smearing or anything else? Or?
Oh, yeah, for sure. On the CCDs, we're oversampling each ground scene 8 times. So you're overcoming that spatial smearing well, and you're getting a pretty nice top hat. There's going to be some modulation transfer function or, overlap, but that's going to be very good. On the SWIR side, we're only doing 1 ground scene per pixel, so you will get much more smearing, and that's spot on. That's exactly right. By spinning fast, doing that TDI, you're getting a high SNR and getting rid of striping, but now, unless you're being really tricky with some other techniques, you're going to get that smearing. And we didn't have the time to fully develop the detectors on the SWIR side. Actually, the tech isn't there. We couldn't find anything fast enough. Is it what?
It wasn't a priority, or is it harder?
It was harder. It's a different material. We're using mercury cadmium telluride, so MERCAD, MCT, and they're inherently not as fast, and they're more tricky to deal with. Yep. Any other questions? All right, thanks.
Sure.